In the previous video, we explored the notion of limit x tends to infinity of f of x. What was the idea of limit x tends to infinity f of x? We were looking at the value of f of x as x gets larger and larger. That's the intuitive idea, right? Now, natural numbers can get larger and larger, but cannot get smaller and smaller. 1 is the smallest natural number that exists, right? So unlike natural numbers, it makes sense to look at what happens to a function f of x as x gets smaller and smaller. So it makes sense to look at the notion of limit x tends to minus infinity f of x. Let us define this notion. Definition. We say f of x converges to L as x tends to minus infinity if for every epsilon there exists a real number x of epsilon such that mod of f of x minus L is less than epsilon for all x less than x of epsilon. So if x is small enough, then f of x is close enough to L. And we can make it arbitrarily close. For whatever epsilon we have, we can do this. That's what it means. As before, we will denote this as limit x tends to minus infinity of f of x. And instead of saying that f of x converges as x tends to infinity, we might say that limit x tends to minus infinity f of x exists. So everything as before, correct? Now we will try to look at something a little bit more complicated. Okay, so we will look at limit x tends to infinity of f of 1 by x. See, till now we were looking at limit x tends to infinity of f of x, right? Now we are going to look at the limit of x tends to infinity f of 1 by x. Conceptually, this is not different from what we have seen so far, because we can look at this as limit x tends to infinity g of x, where g of x is given by f of 1 by x. So conceptually it is not very different, but still let us unravel what this concept would mean in terms of what we have seen already. We say limit x tends to infinity f of 1 by x is equal to L if and only if for every epsilon there exists an n of epsilon such that mod of f of 1 by x minus L is less than epsilon for all x greater than n of epsilon, which is if and only if for every epsilon there exists n of epsilon such that mod of f of 1 by x minus L is less than epsilon for all 0 less than 1 by x less than 1 by n of epsilon. This is if and only if for every epsilon there exists an n of epsilon such that mod of f of y minus L is less than epsilon for all 0 less than y less than 1 by n of epsilon, and we will just call this quantity delta. Let us just clean it up a little bit more. We will write this as for every epsilon there exists an n of epsilon such that mod of f of y minus L is less than epsilon for all 0 less than y less than delta. Let us try to understand this statement a little better. See, what this intuitively means is that when y is close to 0, then f of y is close to L. However, y is not just close to 0, it is also greater than 0. So it's close to 0 but greater than 0. So we say that limit x tends to infinity f of 1 by x is equal to L if f of y is close to L whenever y is close to delta but y is greater than 0. So the proximity to infinity is converted to proximity to 0, but from a particular direction. Which direction? From the right hand side. Now the same thing can be looked for limit x tends to minus infinity of f of 1 by x. We say that limit x tends to minus infinity of f of 1 by x is equal to L if and only if for every epsilon greater than 0 there exists an n of epsilon such that mod of f of 1 by x minus L is less than epsilon for all x less than minus n of epsilon. Which is if and only if for every epsilon greater than 0 there exists an n of epsilon such that mod of f of 1 by x minus L is less than epsilon for all x such that 0 is greater than 1 by x is greater than minus 1 by n of epsilon. Okay, so here x is negative because x is less than minus n of epsilon, and hence 1 by x is also negative. And from x is less than minus n of epsilon, we get that 1 by x is greater than minus 1 by n of epsilon, which is again equivalent to for every epsilon greater than 0, there exists an n of epsilon such that mod of f of y minus L is less than epsilon for all y such that 0 is greater than y is greater than minus 1 by n of epsilon. So if we call this quantity delta, then we can clean this up and say for every epsilon greater than 0, there exists an n of epsilon such that mod of f of y minus L is less than epsilon for all y such that 0 is greater than y is greater than minus delta. Thus we have proved that limit x tends to minus infinity f of 1 by x is L if and only if whenever y is very close to 0 but less than 0, then f of y is very close to L. And we can choose how close we want it to be. And this in some sense is not some magic. I have not taken this out of some hat or something. See what is happening. As x tends to infinity, 1 by x tends to 0. But from which direction is 1 by x tending to 0? It's coming from the right. 1 by x is always positive when if x is tending to infinity. So 1 by x is converging to 0 from... So if this is 0, 1 by x is converging to 0 from this direction. From the right it's coming. On the other hand, when x tends to minus infinity, even then 1 by x converges to 0. But now this time it's coming from this direction. For each negative x, 1 by x is also negative. So 1 by x is less than 0. So this time the function 1 by x is converging to 0 from the left. But what does all these things mean? Together what it means is that even if we start studying only limit x tends to infinity f of x and limit x tends to minus infinity f of x, it will naturally lead us to the notion of limit x tends to 0 of f of x. That means the behavior of f of x near 0. And this is for functions which are not even defined at 0. Even for functions like that, we will have to study about the behavior of the function f near 0. Like for example, the function 1 by x. The function 1 by x is not defined at 0, but we can see what happens to the function 1 by x as x approaches 0. And it's natural to look at this notion. But then 0 is not something really special, right? Because if x converges to 0, then x plus a converges to a. So if you look at the function f of x plus a and take the limit as x tends to 0, then we are looking at the behavior of f near a, right? Because x plus a is near a when x is near 0. So this would be what we will call this quantity or this limit as limit x tends to a of f of x. Hence it's also natural to look at the concept of limit x tends to a f of x. So far what have I done? I have motivated why it is natural to look at the limit of a function as x approaches some value. And we have already, in all these discussions, it is a definition for this notion is hidden. Let us finally define this limit. Definition. For a function f from R to R, we say L is a limit of f at A if for every epsilon greater than 0 there exists a delta greater than 0 such that 0 less than mod of x minus a is less than delta implies that mod of f of x minus L is less than epsilon. We have used all the intuitions we have gained along the way to make this one definition. Please pause and ponder and make sure that you have understood why we have come up with this definition. At this point, you might want to rewatch the previous video and this video so far once more. Make sure that you have understood the motivation for defining the limit of a function as x tends to a very thoroughly. Once you have understood this definition, stare at the definition a bit more, and then you will realize that to define the limit of f at a, you do not need the function to be defined at a. We just need the function to be defined near a. So the function f need not be from R to R. It could be from a smaller, it need not be defined on the entire real line, but it can be defined on a subset of R. And this is what we will make precise next. Definition. Let A be a subset of the real line. A point C in R is a cluster point of A if for every delta greater than 0 there exists at least one point x belongs to A such that 0 is less than mod of x minus c is less than delta. The idea is that we define cluster point because if f is a function from A to R, we can define the limit of f at all cluster points of A. So that is why this cluster point is important for us. Go back to the definition of a limit of f at c and look at the importance of the inequality 0 less than mod of x minus c less than delta. This will help you understand why we need to define something like a cluster point. Even though this definition is directly taken from the definition of limit of f at c, it is really difficult to visualize what a cluster point will look like, right? So to give a better intuition about what a cluster point will look like, we will prove a theorem. A point C is a cluster point of a set A if and only if there exists a sequence an in A such that an is not equal to C and limit n tends to infinity an is equal to C. So a point C is a cluster point of the set A if and only if there are elements in A that converge to the point C. Let us try to prove this. So if C is a cluster point, then there exists x in A such that 0 is less than mod of x minus c is less than 1 by n. For each n we will have such an x. And to show the dependence on n, we will call this xn. Okay. By this we have a sequence xn, and clearly this sequence xn converges to C. Clearly xn converges to C. On the other hand, if there exists a sequence an such that an is not equal to C and limit n tends to infinity of an is equal to C, then for any delta, there exists an n that depends on delta such that 0 is less than mod of an minus c is less than delta for all n greater than n of delta. So because of this, there will be one element at least. Hence, we have proved the theorem. Now we are equipped to give the most general definition of the limit of a function that we will see in this course. So let A be a subset of the set of real numbers, C be a cluster point of A for a function f from A to R. L belong to R is a limit of f at C if for every epsilon greater than 0 there exists a delta that depends on epsilon greater than 0 such that x belongs to A and 0 less than mod of x minus c less than delta implies that mod of f of x minus L is less than epsilon. And in this case, we will say that L is equal to limit x tends to c f of x. That will be the notation we will use. Now we will also talk about divergence of a function. Definition: if L is not a limit of f at C for every L in R, then we say that limit x tends to C f of x does not exist. Notice that for a sequence, the limit was unique. We had proved that the limit of a sequence is unique. But here we have used the word a limit, which kind of suggests that maybe the limit is not unique. But we will prove that that's not the case. We will prove that the limit, if it exists, is indeed unique. That's the next theorem. Let me repeat. If f from A to R is a function and if C is a cluster point of A, then f can have only one limit point. How do we prove this? We prove this by contradiction. This is exactly what we did for the sequences as well. We assume contrary. Let L and L dash be two distinct limits of f at C. Okay, then what do? We look at mod of L minus L dash. But this can be written as mod of L minus f of x plus f of x minus L dash. This is our usual trick, nothing special that has happened. Which by triangle inequality is less than or equal to mod of L minus f of x plus mod of f of x minus L dash. And because L is the limit of f of x, by choosing x close enough to C, I can make this less than or equal to epsilon by 2 and I can make this less than or equal to epsilon by 2. So the sum is less than or equal to epsilon. As epsilon was arbitrary, this implies that mod of L minus L dash is equal to 0. That is, L is equal to L dash, which is a contradiction to the assumption that there exist two distinct limits. Hence, the theorem has to be true. Towards the end of the previous video, we proved that we can think of limit x tends to infinity of f of x in terms of sequences. An analogous theorem is true for limit x tends to c f of x. Let us state this theorem. Let f from a to r and f be a function from a to r, and let c be a cluster point of a. Then the following statements are equivalent. One, limit x tends to c f of x is equal to L. 2, for every sequence xn in A that converges to C such that xn is not equal to C for all n in n, then sequence f of xn converges to L. I will not prove this theorem because the proof is very similar to what we saw in the previous video. So going through the proof again is not going to really help you. So I will give the proof as an homework. So proof is homework. Okay. On the other hand, let me go through once more why this was important, why this theorem was important. This theorem helps us to think of limit of a function as a limit of sequences. Of course, we have to think of limit of multiple sequences, but still, nonetheless, it's a big advantage. The major advantages comes in actually proving theorems. We will show in the next video that almost all the theorems we had for sequences come for free for limits of functions. For example, we can show that if a function has a limit at c, then the function is bounded near c. If f has limit L at c, and if g has limit k at c, then f plus g has limit L plus k at c. Similarly, f minus g has limit L minus k at c. Almost all the limit theorems that we saw for sequences will just come for free. And that is the real power of this theorem. We will do that in the next video.